So as I mentioned yesterday, yesterday's lecture was mostly about single particle physics, preserving quantum coherence, and so on. Today I'm going to give you examples of how we can now integrate atomic interactions into something that's really interesting. You have heard about topological insulators. You have heard about quantum matter, that they can synthesize atoms one at a time. You have certainly heard about quantum magnetism, spin Hamiltonians, and so on. Some of those we will actually be able to explore directly with the clock. And just because of we can preserve the quantum coherence of such a long time scale, even if the interactions are relatively weak in the ordinary sense, they will become a dominant mechanism that governing the dynamics of the system. So hopefully I'll give you some flavors of how experimentally we explore many-body quantum systems from the first principle in this case. So as I said, the lecture outline, the second lecture now is building on the first lecture of understanding all these basic ingredients of maintaining the maximum quantum coherence for single particle physics. And now we're going to introduce the atomic interactions in here to give you some spin Hamiltonians, how we explore those, and then discuss how we study the emergence of complexity from simple ingredients. I'll give you a particular example of spin orbital coupling, synthetic and magnetic field in topological matter, and how we use clock to explore that, and give you some connection back to the quantum measurement, where by understanding many-body physics in a fundamental level, it will help you come back to push the frontiers of a measurement metrology. And again, like yesterday, please always interrupt me, ask questions if you are not following what I'm talking about. It's much more important to have lots of good interactions as we had yesterday throughout the lecture. Even if I cannot finish, I'm a little bit ambitious today. I have like 45 slides, which are a little more complex than yesterday's. But if we don't finish, we still have tomorrow. So let's go on with that. As I mentioned, quantum measurement frontier, as you can think of this as a deceptively simple system where you are using lasers to probe a single atom, this quantum pendulum, and you're putting many, many atoms together. Once you add ingredients of interactions, this starts to become very complex. For example, this is a picture of the quantum magnetism, how the spins are arranging themselves according to how they interact with their neighbors, and how the quantum noise of these interacting quantum particles can become correlated. This obviously connects to the reason why you are here for the summer school, is to so-called learning the absolute frontiers of quantum technology and quantum information science. Some of those have a direct impact or intellectually deeply connected to quantum information science, to advanced materials, to advanced metrology, which can give rise to an array of future important technologies for society, including quantum information processing, but beyond that. Okay, so this is where the motivation comes from of why we start with simple quantum systems like this and gradually move into more complex quantum systems. Yesterday I mentioned, if you remember from yesterday's lecture, we have lasers that have a tremendously long coherence time. This is an example of a laser exhibiting line width on the order of 10 millihertz or so with a coherence time of tens of seconds. And you use a laser like this to probe. Remember I talked about having atoms confined in a one-dimensional optical lattice where you have individual atoms confined in these individual pancakes, and you have lots of atoms working together and they're interacting with each other. When we do spectroscopy using lasers like this to explore the atomic absorption line shape, what you find out is the line width is actually broadened to something which is much broader than the laser line width. It is also much broader than the line width I was telling you about. It was supposed to be 10 millihertz or 1 millihertz, but yet experimentally we see something that's much broader. And it's not because we didn't spend enough time on it. We actually try to make the excitation laser to last for a long period of time. So it's so-called Fourier limit, where the time, as the probe time window gets longer and longer, in principle, your spectroscopy resolution gets better and better. But contrary to what you would expect, as you go to longer probe time, that you expect the line width to get narrower. Here you see the line width gets not only broader, but also get distorted. And this is a clear signature that interaction is playing a big role. And as you wait longer, the atoms become more interactive and they become entangled on top of each other. And that's why the excitation exhibit a fairly complex spectrum. And this is the first signature that we know we are probing something which is a many-body physics. And so before I tell you about the basic ingredients of how two particles interact with each other, two fermions, let me refresh you in terms of the basic quantum mechanics on how that governs the fermions or bosons. We know that in the strontium atom, as I lectured yesterday, there are three basic degrees of freedom. Electronic, meaning you're going from the ground state to the excited state. Remember we talked about those as pseudo-spin halves degrees of freedom. There's a real nuclear spin degrees of freedom with 10 different nuclear spin states. These 2 degrees of freedom largely do not influence each other because I dot j equals to 0. J is the total electronic angular momentum. Since that quantity is 0, the I dot j equals to 0. So you can argue there's no hyperfine interactions. So the nuclear degrees of freedom will play an important role to dictate quantum statistics, but it wouldn't influence how the atoms are interacting with each other electronically. And there's a third degrees of freedom, which is motional degrees of freedom. These atoms are confined in optical lattices. Their motional states are quantized. And say I have 2 particles, one occupying quantum state m in the motional degrees of freedom, the other one's n. And you can have 2 different ways. You can spatially symmetrize the wave function, the nm plus mn, or it can be anti-symmetrized, and it's so-called S wave and P wave. So we know that when you write down a quantum mechanical wave function describing the 2 particles, because the particle is a fermion, its total wave function has to be anti-symmetrized. So you have a nuclear degrees of freedom where you can have 2 nuclear spins to be between 2 atoms. Can be so-called a spin triplet or spin singlet, which is symmetrized and anti-symmetrized. Product with electronic degrees of freedom, again, you can have a spin singlet, spin triplet, spin singlet, or the motional degrees of freedom where you can have a symmetrized S wave or anti-symmetrized P wave. The requirement is that by the end of the day, the total wave function has to have a negative sign with respect to exchange of the 2 particles because those are fermions. And that means either one of the wave functions has to be anti-symmetrized. It can come from nuclear spin or electronic spin or from motional degrees of freedom, or all 3 of those has to be anti-symmetrized. So in the case of some simple experiments we can start, let's put all the nuclear spins in the symmetrized manifold. For example, by polarizing the entire ensemble into a single nuclear spin state. So that degrees of freedom is gone. Electronic degrees of freedom, suppose they are all starting from the ground state and you excite them exactly the same way. So the 2 spins will remain in the so-called triplet manifold, spin symmetrized manifold. Then the only other degrees of freedom that can be anti-symmetrized is the motional degrees of freedom. That's where the interaction can come from. The people have heard P wave interactions. That's what a P wave interaction is, the negative sign. Okay, so now we have these atoms confined in a single pancake of two-dimensional optical lattice. Along the direction of this vertical direction, the confinement is exceedingly strong. So the motional states are in the absolute bottom of the ground state along z direction, the vertical direction. However, along the transverse direction, xy direction, the trap is relatively shallow. This just feels like it's a piece of paper where atoms are trapped in there. And because these trapping frequencies are relatively small, at a temperature of a few hundred nanokelvins or microkelvin, you're still occupying many different motional states here in the xy direction. Essentially, the particles are still moving in the 2-dimensional traps like this. And they can interact through, as I was just explaining to you, these spins, the pseudo-spin half systems being driven on the block sphere because it's you have a 2 internal quantum mechanical state. So if that's symmetrized, then the motional degrees of freedom has to be anti-symmetrized. This is so-called P-wave interactions. The interaction is rather weak, but if you have very long coherence time, these interactions will dominate the system dynamics. In another way of thinking of this, these are the bare energy states of the atom, ground state, 2 atoms, because you have 2 atoms, ground atom, 1 atom in the excited, 1 atom is in ground state. and both atoms in excited state. Those are the energy manifolds of the previous energy manifolds, but then they are shifted due to the fact these particles can interact with each other. And this is the so-called contact interaction arising from microscopic picture of two atoms essentially running into each other. When they get close to each other, there's the van der Waals interactions that will give rise to how the atoms can interact with each other. So now, this leads to this 1D lattice clock spin model, where if we describe each spin is a half. If we have n particles, the total collective spin in the system is n over 2. And because you're driving the spins with a laser, so the laser can be detuned from the resonance. This is the delta SZ term. Omega Sx is just how the laser is driving the spin, so-called Rabi frequency, going from the south pole to the north pole. It's rotating around this omega frequency, which is a Rabi frequency. And the S-wave interactions that I was introducing earlier in the previous slide gives rise to these two terms. So one is SZ times SZ term. This actually turns out to be a nonlinear term that can correlate the quantum noise of all the spins in your pancake trap. And there's also a SZ linear term. That these two terms are coming from the fact these particles are interacting with each other. And if it's P wave that's temperature independent in the two-dimensional subspace, then you can actually give rise to this collective coupling chi. This is this basic spin Hamiltonian describing this 1D optical lattice clock. Yeah?
So do you assume they are on the same like orbital wave function?
Each one of them has its own energy eigenstate, and the interaction is relatively weak, so that such that each particle is actually occupying the same energy eigenstate. They're not changing, but they can interact as a perturbation with each other. So the wave function is just described by a particular orbital. So say this atom is here, that atom is there, and you have a wave function to describe this quantum state describing that quantum state. And it turns out this atom interacting with that one, or this atom interacting with this one, has a very weak dependence on the indices of which n number you are reciting. That's why it actually turns into a collective interaction. It's not exactly strictly true, but it's approximately true. Okay, and these parameters, this nonlinear spin-spin interaction parameters, give rise to exactly this so-called P-wave interaction. How the excited state gets shifted, or the intermediate state gets shifted, or ground state gets shifted. These are basic ingredients of the two-particle interaction given by the van der Waals interaction potentials. And they now enter into this many-body Hamiltonian, where these terms, which are governing two-particle interactions, now are describing the coefficient sitting in front of a collective spin SZ component through the nonlinear term and through the linear term. So you can actually study the spin Hamiltonian and use that to figure out how the two particles actually interact with each other. Or seemingly very simple two-particle interaction energy can give rise to very complex quantum state evolution when you have lots of particles in there. This is the basic ingredient that we want to have. In principle, we want to have, you only have two particles in there, and you can understand how they interact. You put 3, 4, 5. You want to understand things evolve from very simple ingredients to something very complex. And this is what we are particularly good at in the laboratory, because we can control these quantum states, as I lectured yesterday, maintaining maximum quantum coherence on single particles. Now I can put one particle in at a time and study the emergence of the complexity. And if you like mathematical modeling, this is actually a perfect example to draw an analogy to a double well system. Imagine you have a BEC on the left well and another BEC in the right well. The particles are interacting through the ground, the VGG, what I described as how the particles interact with each other in the ground state. You can think of the particle interacting with each other on the left well. And the excited state can be thought of as a right well. And they are coupled between ground and excited state through this Rabi frequency, because that's how the spin half is being flipped by the Rabi frequency, omega. Here you can think of this, visualize this as a tunneling from left to right, right to left. And this Hamiltonian described, if you put two kinds of atom ensembles on the left well and the right well with a little bit of a detuning data between these two traps with some coupling, tunneling coupling omega with the on-site interactions and so on is described exactly by the same spin half Hamiltonians that I wrote here. So oftentimes, depending on what particular experimental systems you're working on, you can use one particular mathematical model to describe the evolution of your quantum system. This is the essence of quantum simulation, that we do experiments in cold atom physics, and some of the Hamiltonian we study is exactly what's governing some of the outstanding problems in condensed matter physics. Okay, so the consequence of doing this is, imagine these atoms are confined in this one single pancake, and they are being evolved due to the lasers driving them, going from the south pole to the north pole. And remember that this is what I explained yesterday. This is the quantum noise of each individual spin. It never is very sharp. There's a 1 unit of a quantum noise there. And if you wait after you're driving each individual spins onto the equatorial plane, so that means you are in the coherent superposition between the ground and excited state. And then you just wait there for these particles to interact with each other. And because of it, even though the interaction energy U, due to the p-wave interaction, remind you with this Hamiltonian chi SZ square term, if this U, which is characterized by chi, is relatively small, but if time t is very long, eventually you get these particles into the entanglement, and you can actually see the spin noise gets distorted. Now you become a collective spin noise. In fact, it's shifted away from the original symmetrical state. You can see the minimum of the spin noise is no longer at a 0 degree, and it's distorted into elliptical shaped spin noise. If you look at a particular axis, you can actually see spin noise goes much bigger in certain quadrature, much smaller in the other quadrature, and so on. And the point I want to emphasize is you waited long enough that because the single particle coherence is so good, even though the interaction is rather weak, these quantum noises of individual particles are now correlated. And that's something you can directly measure through the clock spectroscopy.
Can I ask a question?
Yes. Yes.
So that is a Bloch sphere of the total spin of the system?
Yes, that's correct.
So I don't understand why this gets
distorted. It's because of this term chi SZ square, and SZ is a vector along, it's basically the projection of the total spin along the z direction. But the chi SZ square term meaning like you can have the SZ, which is moving above the equatorial plane, will have the spin moves a little bit to the right, while if the spin is actually still below the equatorial plane, it moves to the left. And people call it a single axis twist. So essentially you move the spin to the equatorial plane and they stretch them out like that. And that's the reason why this quantum noise becomes correlated between these different interactions.
And this is like a mean field approximation to the
Yeah. This is a mean field, but actually what we observe actually physics beyond mean field. So this is an excellent question. Right now this picture is a mean field picture, but then by the time you start to talk about individual spins, the mean field is mostly describing the mean collective vector, how they evolve. But when you talk about individual quantum noise, then it's a beyond mean field. Other questions? Yeah.
Sorry, so I'm a bit confused about dimensionality. So you have a 2D, should I think about 2D cross section, or is it like I confined enough that I can approximate? So you have a 1D model, right? And then you actually mean field. So
What do you mean? So let's be careful when you say 1D or 2D. The spatial confinement is 2D, is two-dimensional, and along the direction of a z, the quantum state is completely frozen, and they are only evolving in the xy direction. So that, in that sense, the spatial dimension is 2D.
no, because you gave a model that's 1D.
Oh, I'm sorry for that. Maybe the language confusion. That when I say one-dimensional lattice just means there's only one optical beam gets retroreflected, and what you form is a stack of pancakes, which are two-dimensional traps. So sorry for the confusion. Is that clear, or you're still confused? You were confused with the language of a 1D lattice, right? I think that you were confused by this particular title, 1D lattice clock.
Yeah.
Yeah, so this 1D is, I'm sorry for being not so careful. This is 1D, meaning one-dimensional lattice. When the lattice is one-dimensional, meaning the laser is, for example, the laser beam is going this direction, and this is 1D. And if I put a mirror here, this is sinusoidal wave coming in, and it gets retroreflected. You start to form standing waves.
Yeah.
Yes, and that's from that sense I'm saying it's a 1D because there's only one-dimensional lasers forming standing wave, and because of that, you form individual pancakes. Yeah. And these pancakes are two-dimensional object.
Yeah. And in the model, there's no kinetic energy. That's what's the other thing.
Okay.
Is in,
Kinetic energy is because they are so that's what Liang was asking, that these interactions are actually quite weak between these particles, and each individual particle in fact is confined to a particular energy, eigenenergy of the trap, and they are preserved in fact. So you can think of the particles just oscillating back and forth on the prescribed trajectory inside of the harmonic oscillator. We are interacting, but our interaction is rather weak. So the kinetic energy doesn't change. What the interaction affects is how you are spinning, you're moving your head, even though you're still sitting on your chair. Does that make sense? So kinetic energy doesn't change because my interaction is actually rather weak in that sense.
compared to the confinement energy.
Yes, exactly.
So
Compared to,
otherwise,
that's correct. That's exactly right. Not only compared to the confinement energy, compared to the harmonic frequency of separation. Like these separations are few hundred, so give you a quantitative number. The separation from this harmonic level to that harmonic level, say, is 500 hertz times h. H is a Planck constant. The interaction between these particles is actually about a factor of 100 weaker. So they are still confined in their harmonic levels, but because of their rubbing shoulders back and forth, eventually how they turn their angles in their internal degrees of freedom gets influenced. That's why we can reduce this down to a simple spin Hamiltonian. Yeah, excellent questions. Yeah. Can you say it again? How do we confine? It's just when you have maybe I should draw this. I wasn't doing a very good job here. If you think of you have a sinusoidal wave coming in, right, and it gets reflected, such that you can see that there's a standing wave that's forming. So there's a places where you have oscillation, which is the electrical field is oscillating crazy, and there's a place which is called a node. There's no electric field, and then here you have an anti-node again, right? These are the standing waves you have seen from your introductory physics class. The particles at the center here, you have a very large electrical field. It's going to remember I talked about polarization of the atoms due to the light. This is where the atom gets polarized the most, and that's where so you can visualize this as a trapping potential, and then by here you have no trap, but then the next trap is here, next trap is here, and so on. So atoms are trapped in these regions because that's where the standing wave amplitudes are. When at the anti-node there's no electrical field, the atoms won't be trapped. So those are the pancakes. This is what I was talking about, a stack of pancakes.
So my question is how within each node it's like confined in this plane direction.
Oh, so you're saying how does the confinement in the transverse direction is coming from? Sorry about that. And that's because this beam coming in is a Gaussian beam. Just like this laser has a finite beam waist. So if I had a mirror here, which would be dangerous too because the laser light will be reflecting to your eyes. But otherwise, I shoot this laser beam onto a mirror, it's going to form a standing wave along this direction. But the beam confinement is confined by the beam waist radius of this visible beam that you saw. So it will be as big as that beam right there. That's the pancake size, transverse direction. Does that make sense? I don't know. I'm not a very good drawer. Laser beam looks like this. It's a cylinder that's propagating. So now you can have pancakes like that, right? The atoms are being confined in the transverse direction, which you call X and Y. In the Z direction, you have these interference patterns. That's where that's coming from. e to the I k z, and then you put it, and you have e to the minus I k z coming back. You form standing waves in the z direction. But in front of this, you have the e to the, usually you have the r over x squared plus y squared over beam waist squared. This describes the spatial profile in the transverse direction. Does that make sense? Okay, this is really, if you have learned electromagnetic waves propagating in space, this should not be difficult to understand, right? Yes?
So in the Hamiltonian, the atom number enters, so usually how well is this calibrated, and does that have like a dephasing-like effect if one runs around that substrate?
The atom number can be calibrated exceedingly well. We can, for example, remember I told you yesterday there's a quantum certainty principle and uncertainty principle. You can put all the atoms all in the ground state. There's no noise, and you can count them, all of them. So they can be calibrated to within 1% or less. Okay. So we'll keep going. Somebody was very, very kind turning on the light. Maybe you can turn off the light again for me. Thank you very much. Just to give you a little bit better image quality. And when we needed to use Blackboard again, I will ask you for help. So I just described this particular way of describing this excuse me, 1D lattice called two-dimensional trapping potential spin Hamiltonian, which is this guy. And I was just finishing talking about how the quantum noise becomes correlated. And when we set up doing the clock, this was not our initial goal. Our initial goal was to build a system where the particles do not interact, right? So we did not anticipate this. When I started building atomic clock in 1999, when I started my faculty job, certainly I did not anticipate I would be studying spin Hamiltonian. But this is actually a pleasure of doing science, is as you go on, do something, you figure out, well, there's a problem. Because at the time in 2008, when we start to figure out their problems, was because our clock frequency gets shifted due to these particles being interacting. And we have to solve this problem, otherwise the clock won't be accurate. And on the other hand, solving this problem turns out to be intellectually very rich. And this is really the pleasure of doing science, experimental science particularly, that sometimes you just don't have a particular manual textbook written for you, and you go explore and discover new things. And what we discovered was the frequency, indeed, the clock frequency that I was telling you yesterday, super accurate, 10 to minus 18 and so on. But when the particles was interacting, what we find the frequency actually is shifting at a 10 to minus 15 level, depending on the angle of how you're driving the spin from south pole to the north pole. This is the polar angle theta. And this is the block sphere. So this is obviously not something acceptable. The frequency, you're making atomic clock. You're supposed to tell people what that frequency is. And here I'm telling you the frequency depends on the spin angle, and that's not acceptable. And you can say, well, but you did find a particular spin angle where the frequency shift is 0. So maybe you can just operate your clock here. And some people do that after we discovered those facts. But even here, the fact that these particles are interacting, remember I showed you the line shape when I said my laser is really good, but I cannot recover a very nice line shape. That's because even though the shift, mean field shift is 0, the particles are still interacting strongly. The quantum noise is still blocking you from reaching very good accuracy. So this is actually the problem that we find out to be in this one-dimensional optical lattice. Later on, we work on three-dimensional optical lattice to solve this problem. But what's satisfying is that you can actually, using the frequency measurement like this is a trivial, in some sense, of a spectroscopy measurement, and use this slope and where the intersecting point is, you can deduce all these parameters of how two particles were actually interacting with each other. The entire van der Waals potential of two particles, how they interact with each other, now you can fundamentally measure with very, very high accuracy. So these are no longer abstract concept that you calculate a mathematical formula, but it's actually a real physical quantity that has a lot of physical meanings because it influences how the clock frequency will shift, and we can measure that very precisely. And this is remember that I told you this is the so-called the twist term, the chi-square term, the chi-SZ square term, this is the linear term, and so on. So that all this can be measured very precisely. Another thing that I want to give you just a quick teasing because it's kind of interesting, the so-called SEON symmetry. You probably have heard of the term, but here, let me explain that to you a little bit. Remember we talked about there's two different spins, the pseudo spin half and the real spin nuclear spin 10 states, but I dot j equals to 0. That means that these nuclear spin states could be there, but in principle they do not influence how the atoms interact with each other, right? Because I dot j equals to 0. So that means that if I force myself to have atoms all occupying in this particular nuclear spin state, and I'll look at the clock frequency shift, and then I put some spectator atoms at a different other nuclear spin states, they should be symmetrical in regard of how they interact with the particle that's being interrogated in your clock sequence. So what do I mean by this colorful assembly of different nuclear spin distributions can be varied. And when you measure the actual frequency shift, it would not care whether you had this type of distribution or whether you had this type of distribution. It really shouldn't matter because these nuclear spins were not interacting with electronic spin directly. They only play a role as through the quantum statistics. When you try to symmetrize wave functions, these nuclear spins are important. But whether you are in the 5½ state or -5½ state or -9½ state, it really doesn't matter. It only cared about nuclear spins. So you can test that kind of SEON symmetry. This, by the way, is the SEON symmetry people in high energy physics, in particle physics uses. And you can test that by looking at the frequency shift. This is the same frequency shift that I was telling you about depending on this polar angle. So if I always look at the clock of these black atoms here, and you have the other atoms which are playing a spectator role, you can see depending on whatever the distribution of nuclear spin states you have, they all collapse onto a single curve, experimental curve that you measure. It's a very powerful measurement of the so-called SEON symmetry. So it sounds very simple, but it's actually quite interesting, unique observation of this. Some of the condensed matter physics would actually rely on SEON physics to realize unique Kondo lattice and so on. So far, the interactions are confined in a single pancake, as I was explaining how the pancakes are made. This is the picture again. These are basically, you can think of the anti-node of the standing wave. Particles are confined in those standing waves. If this well is extremely deep, the particles have no chance to tunnel back and forth. Then essentially what you're studying is the isolated systems of this pancake, that pancake, that pancake. Okay, no tunneling. Now, what if you let them, the lattice actually being weakened, or the laser beam gets weaker? Now the trapping potential gets smaller. Eventually, it becomes so weak that the lattice, the atom can start to tunnel, just like an ordinary lattice. You have a block wave functions to describe the quasi-momentums, and the particle can start to move around between the enabling sites. And that interaction is going to introduce something really, really interesting, because previously I was describing how the atoms interact with each other within the same pancake. But once the pancake can become tunneled, tunneling is allowed between pancakes, particles can go from one to the next, and they may be perceived as being foreign. From previous pancake going to the next pancake, these particles are being tagged by the local atoms sitting in this pancake, who knows where the atom is coming from. So this will change the nature of how they interact with each other. And this actually goes to this quantum simulation wish list, right? You have some of you must have heard about quantum simulation sitting in this class. For quantum, it's part of the big part of the quantum information science. We want to use, say, cold atoms to simulate condensed matter system. What's condensed matter system? You have a charge, you can have a motion, electrons can have motion, they have a spin, they can have interactions. That's the 4 ingredients in normal condensed matter model when you build. And we know, depending on the different ingredients you have, for example, you put a charge motion together, you can have a quantum Hall effect. You put a motion interaction charge together, you can have fractional quantum Hall effect. You can have a motion and an interaction together, you can have a Kondo physics with spin, and so on. Spin and interaction together will become or give rise to magnetism. So these are the various condensed matter phenomena of quantum physics manifesting themselves in the many-body physics when you have these ingredients. And in our optical lattice clock, so far I have told you about some ingredients of interactions and spins, right? So you can already explore some rich physics like magnetism and so on, the spin half Hamiltonian. But what if we also open up motion? If this also becomes available, which is a tunneling, then the phase space you can explore becomes much richer. And in fact, sometimes you can even use spin to so in order to put all these three together, you introduce this so-called spin orbital coupling, where spin and motion are going to be coupled together under interaction. And this will give rise to really interesting phenomena already. But you can also think of the way that instead of a spin, you can also think of as a synthetic gauge fields, you can think of as a charge. And so instead of a spin orbital coupling, you can think of you're introducing synthetic magnetic field in your system. I was told that you had heard earlier lectures about interplay of these different ingredients gave rise to synthetic material. And let's see, we can actually, if we can experimentally explore some of those, even at the beginning level. So remember, that's what I was telling you about. We have optical lattices like this, and when I drive my transition from the ground state to the excited state, I'm going from ground G to the E excited state, but I'm doing that on individual pancakes. Each little sinusoidal wave represents a trapping potential, right? Now, if the trapping potential is weakened, suddenly you start to see a band structure emerge because the particle cannot start to tunnel. And what's really interesting is that the wavelength that governs the trapping potential, remember, was given by the so-called magic wavelength. I explained that to you yesterday. That wavelength is fixed. The laser that's probing the clock transition, on the other hand, works on a different wavelength. Because this is given by nature. The strontium atom has this atomic properties. And so that wavelength is not commensurate with the lattice spacing because those two wavelengths are not equal to each other. So when the atom is being driven from down here to the excited state up there, it accumulates a phase shift phi. In the neighboring site, the phase shift is 2 phi. The next neighboring site, the phase shift is 3 phi. The phi is just e to the I kx. K is the wave vector of the laser, the clock laser. X is the position of where the atoms are located. And this is e to the I kx is not integer of 2 pi. Therefore, you have this phase shift phi. And that phase shift varies from one side to the next to the next. This phase shift is what's distinguishing atoms. If this atom tunnels from this side to the next side, you can tell this atom is different because the phase evolution due to the laser is different. This is where the interaction becomes very interesting, because previously when the particles are only interacting with each other within the same lattice, everybody is indistinguishable, so it's a p-wave interaction. Now when the foreign particle comes in from other neighboring sites, which you can tell because their phase evolution is different, they have a phase print on them, then the interaction can be both S-wave and p-wave. Yes? Does that make sense? Okay, so in fact, what we can see in the experiment is this is the cartoonish picture that some of the publication office made for us. You can actually see the clock gets distorted because there's so-called, have you heard about topological surface currents? You can drive atoms into coherent superposition, and if the atom is in the ground state, it wants to go to the left. In the excited state, it wants to go to the right, and it gets stretched. It looks like that. And this is because of the spin and orbit is now coupled to each other. How the spin evolution depends on their quasi-momentum in the optical lattice. So this is the basic ingredients that we can study, is the spin orbital coupling. But I can also explain this through another angle. It's so-called synthetic magnetic fields. So again, remember, this is the standing wave of the 813 nanometer one-dimensional optical lattice forming two-dimensional pancakes. These are the side indices 1 through n. And you can use the synthetic dimension, the ground state and excited state, as if you are forming a two-dimensional lattice. One dimension is along the spatial dimension, the other dimension is through the internal states, ground and excited. Now, what are the consequences? I explained to you, due to the fact that the wavelength is mismatched between the clock laser and the lattice spatial separations, you pick up a phase shift every time you go to the neighboring site. You pick up this extra phase shift phi. And this phase shift phi is nothing but the ratio of the two wavelengths. One is what you use to probe clock. The other one is what you use to confine the atoms in the lattice. So now, plus the tunneling. So now you can actually simplify the problem. This is now simplified into a single plaquette. This is lattice site 1, 0, lattice site 1. This is the ground state, this is excited state. So let's say we start atom in the lattice site number 1 with atoms in the ground state. I can drive laser with the omega 0 e to the I phi. This is the Rabi frequency, drive the atom from the ground state to the excited state, right? And you pick up a phase shift phi. Now this atom in the excited state can tunnel to the lattice site on the left-hand side, and there's no phase shift, it's just tunneling. And once it's here, the laser can drive it back down from excited state to the ground state. Here, this phase shift doesn't have the e to the I phi because it's the side of 0. And then once you get to the n equals to 0, you can tunnel back. And through this entire process, you started from initial condition here. Through this plaquette evolution, you're coming back to the initial condition, except you have picked up this phase phi. And this phase phi you can think of as a synthetic flux going through this plaquette, and you can assign this to a synthetic magnetic field, a fictitious magnetic field. So this is where synthetic magnetic fields arises in this very simple spin orbital coupling picture.
So still we are assuming that each pancake harmony that is much stronger than this other.
Still, I'm assuming, sorry again. Here I'm talking about single particle physics. There's no interaction at the moment. I'm just describing when the lattice site is weak enough, the particle can jump. So all I said is you start to have a particle being able to tunnel back and forth between these lattice sites. And I just isolated. Remember, this is the picture I was trying to introduce to you. There's two rungs, and these are basically the two internal states, and these are lattice indexes according to along the z direction. And I just isolated one single plaquette, 4 sites, these 4 here, and I just evolved this process for you by driving the laser up, going through the tunneling. The laser drives it back down to the spin 0, tunneling again. You're back to the original quantum state, except you have picked up this phase phi.
But if the barrier is lowered, then the combining strengths in each plane will also be weaker, right?
No, not necessarily. They can be completely separated. You can actually lower the barrier in the z direction without reducing the confinement in the xy direction. You can have those separated. I didn't tell you how we did do that, but believe me, we can do those to separate control. So this is the synthetic phase phi that I would just introduce to you, and this is a very simple quantity, which is a pi times the ratio of the two wavelengths, right? And so now you have this synthetic magnetic field in your system, and going back, so you can either think of this as you have a fictitious magnetic field now driving the spin due to the spin orbital coupling. It's like the spin evolution and the quasi-momentum is not coupled. Or you can come back to think about in the band structure in the optical lattice. And I don't know if you have gone through a class of optical lattice or not. Is this maybe too deep? Not through the summer school. So it requires some very basic knowledge of solid state physics, where if the atoms are confined in a periodic potential, you can write down the wave function where you have a periodic part and the phase shift phase part. And if the potential is extremely deep, then the band are so-called insulating. They are flat. If the confinement is not so strong, then they can be tunneling or semiconducting. And there's a so-called bandwidth, tunneling bandwidth that describes the band structure. So previously, when the lattice is extremely deep, you can think of the J, the tunneling factor J is equal to 0. And that means this band is flat, and the top band, the lower band is flat. But if the lattice is now weak, that you actually can't have tunneling exist. in your system, then the band structure is not curved. And I'm only plotting quasi-momentum from minus pi to plus pi because it's a periodic system. So I don't need to confine myself to the first Brillouin zone of the quasi-momentum. Yes?
So you have also other bands?
Yeah, you have higher bands. Yes, so I'm only talking about the lowest band here.
And you can resolve everything?
Yeah, we can resolve everything. Yeah, this is what's very beautiful about this is we can load all our atoms in the lowest possible motional band, and we can promote them to higher bands if we wanted it with laser in a coherent, controlled fashion. This is, again, going back to the lecture I gave yesterday. Like when we were driving atom from ground state to the excited state, you have the freedom of also driving them to different bands. This is something solid state people don't have, right? You wanted to have all different quantum states. I mentioned the 3 degrees of freedom: internal states, nuclear spin, electronic spin, emotional degrees of freedom. All of them are under control by our lasers, and that's the powerfulness of cold atom physics, because you can just drive and change the parameters and so on. So indeed, I'm only just describing the lowest possible band, but we actually, in the experiment, we actually drive them to so that's what n equals to 0 mean. It's the lowest band. But we can also drive them into n equals to 1, n equals to 2, and so on. In fact, we do that in the paper that we published on the spin orbital coupling. Other questions? I understand this may be a little advanced, maybe too advanced. All right. So when you are driving this from one quantum state to the next quantum state, the photon has momentum. Yesterday I described there's no photon momentum, and that's because the band structure is totally flat. But here we actually are picking up a quasi-momentum kick due to the fact that the photon actually has a momentum. And that quasi-momentum kick is, again, the ratio of the lattice wavelength over the clock laser wavelength. And so if you transform this, if you do a gauge transformation, you can think of, like, if you want to insist that the transition is going from along the vertical direction from one quasi-momentum to the other, what I did is just a gauge transformation, insist on the quasi-momentum not being changing. Then the band structure changes. I just shifted the band a little bit. And now you can see the transition, the clock laser. Remember yesterday I made a huge effort to try to tell you that I want my transition frequency of the clock laser independent of the trapping potential. This was a key point of the magical wavelength. And somebody was asking me the question about, well, what if I want them to be different? And remember we were saying, oh, you can use different wavelengths other than the magical wavelengths. You can make those transition to be different. Here, all I did is still working at a magical wavelength. Still if you don't drive it, the trapping potential looks exactly the same for the ground state and excited state. But just because now there's a possibility for tunneling, and you have to accommodate the photon momentum kick, then effectively the drive is not depending on which quasi-momentum you have. The transition frequency is different from the original clock transition frequency. Yes? That makes sense, yes? From quasi-momentum point of view. Okay. So you can now write down your Hamiltonian of how you drive it. You still have the Rabi frequency driving, swinging the spin from the south pole to the north pole. You still have the original laser frequency detuning from the bare atomic two-level system, but now you have this extra detuning delta EQ, which is due to the fact that these bands now have curvatures. And delta EQ is a function of basically the quasi-momentum plus this extra phase shift phi that I introduced earlier. And so if you think about this, this is the concept of there's a effective magnetic field. Remember, this is the same thing that I was talking about, synthetic flux, which gives rise to a synthetic magnetic field, dot spin, and this is how the spin is going to evolve under this effective magnetic field. That's really, there's no magnetic field. It's a laser introduced a geometrical phase shift, and you can interpret it this as if there's an effective magnetic field. So this Bloch sphere now is going to look very funny because how the spin evolves depends on what quasi-momentum you have. Some of the quasi-momentum, you will be very far off resonance from the transition. Some quasi-momentum, you will be exactly on resonance, and so on. So when I start to evolve, instead of every spin goes up the same way, now the spins are evolving quite differently depending on their quasi-momentum. And this is called a spin motion locking. How the spin evolves depends on how the particle is moving, just like how electron moves under magnetic field, right? This is just translating some of the theoretical knowledge you have learned about synthetic quantum matter and so on into experimentally we can visualize this. Okay, and this is the spin locking, motion locking is described through this term B dot S, and this B is a synthetic magnetic field. They all come about due to the fact that you have this phase phi. Otherwise, this term equals to 0. And you can actually directly measure this beautiful Rabi evolution of the spin motion lock. And I think maybe I would, in fact, if you introduce interactions, you will actually find here, this picture is these particles are not interacting. So these are just the individual particles. They're distributed at different quasi-momentum, and they're evolving at a different way. So each trace represents a different particle. But imagine these particles start to interact. And what you will find really interesting is these particles, they want to disperse. As you can tell, some of them are running faster, some of them are running slower. Just like on the trajectory you're running Tour de France or something, you have a course they're running, you're riding a bike, and some faster riders can go ahead and then compared to slower ones. But if you somehow make them interact, the dynamics is much more interesting. Like you're pushing your competitors down the bike and so on. So this is actually, you can just imagine, right? And I'm not going to actually give you, I have a couple slides, but I feel maybe it's a little too advanced, so I'm going to bypass those two. But I want to give you this sort of a direct visualization of how interesting things can be. Just by doing this extra laser phase shift, I started to be able to have a spin motional coupling. And if the particles were interacting with each other, you can see there's a very much complex systems will be arising just by doing that in a clock system. Yeah.
So if you look at this orange line, it's not like just oscillating. It's kind of go up and slow. And
yeah, that's because it's taking some trajectories where it's a still single particle. Here there's no interaction, but it's just a particular quasi-momentum that the trajectory is a little strange. It's like it wants to settle, but then it picks up the oscillation again.
Is Q fixed for each of the
Q is fixed, yes.
So then it's just like a two-level system.
Yeah, it's like a two-level system, yes.
Then why don't we see like just a single?
Just a single, yeah, and you can see that it. For example, even the green curve, right? It's not a single Rabi, it's not a simple Rabi oscillation. It's because of the yes. In this case, the Q has a diffusion, so it's a fixed, but it has a little bit of a diffusion. So we introduced a little bit of a diffusion term, but we in fact, when we first did this experiment, the lattice had a little tilt, so the Q was driven by the gravity, and there's a block oscillation going on. But we actually removed that gravity completely, so the Q is preserved, except over the time scale of the evolution, the Q is a diffusion. There's some diffusion of the Q.
The spread of the processing axis.
Yeah. Okay. So I'm not. Yes, there was another question.
To make sure, right now you are neglecting interaction between.
Yes. Right now this is no interaction whatsoever. But the next two slides was actually going to tell you about interactions, but I decided not to tell you. Yes, exactly. So, right now I'm just describing if you had only one particle, you put it in this particular band structure, how that particle is going to evolve. But now you put more and more particles in, as you would do in condensed matter, then you'll give rise to, like we said, going back to pictures. Let me go back quite a bit into this overlying picture of how the interaction comes about. If you don't have interactions, if you just have charge and motion, you can still study quantum Hall effects and things like that, right? But if you want to study fractional quantum Hall, you want to study magnetism, you want to study Kondo physics, then you have to introduce interactions. So, And that's the reason, this just adds another layer of complexity to the emerging quantum phenomena. So interaction in our clock is always there. It's not like I can turn off, turn on. Well, what I can control is a particle number. Somebody asked, you can control one particle, two particles. If I had only put one particle in my clock, the clock won't be very good, but there will be no interaction. But as I put more and more particles in there, there will be interactions. And that's why we are very interested in studying. Because just for the sake of a clock, you have to study them. But also, intrinsically, on its own, it's a very interesting to study. Yes? Other questions? Yeah.
I was wondering if you could do the same thing that you did here with spin and orbit. Instead of spin and orbit, maybe could you do it just with the motional degrees of freedom? Like I'm always in the ground state, but I have different bands.
Yes.
And then they have different dispersions.
Yes, that's correct. Yeah, in fact, as you go to different emotional bands, they have different tunnelings. So if you have, if you have no tunneling, then everything is boring because the band will all be flat, and regardless of which band you go on to, they're just an index for you, but they are not governing the physics that's going to evolve. But if there's a tunneling, as you go to different bands, the tunneling rate can be very different, and you can actually couple many different bands together. That's the emotional degrees of freedom you have available to you, indeed.
So if I pick two, I would see the similar
Yeah.
effective magnetic
Yes,
field.
that's right. So we haven't done that yet, but in fact, there are already theoretical proposals where you can actually drive different bands to be coupled together. Yeah, excellent point. So when this echoes the point I was making yesterday, when you can control your quantum systems, you go to the lowest level of being able to control your full quantum system, then you can add more complexity into the system under the controlled fashion, and then you will never feel like you're losing control. You're always, so the system is always under your control, and you can put more complexity into it. Okay, so maybe this is good enough about spin orbital coupling. And just to tell you that something that's really exciting that's going on in the lab, in fact, this week, we can actually take images of how these spins are evolving, and when they interact with each other, it's really very exciting. You can actually see striped faces coming out in the clock directly by taking image of the atoms. Anyway, so these are the two slides supposed to show you about interaction, so I'm going to bypass it. I'm going right into the final subject I want to tell you in the remaining 20 minutes or so, which is these interactions have been fun to study, but if you say, my true calling is to really build the best atomic clock ever, then you will say, well, those one-dimensional lattice or two-dimensional pancakes of a stack of them may not be the best because these particles are interacting with each other. So let's go for a three-dimensional lattice now. And again, the language could be confusing. When I say three-dimensional lattice, meaning there are now three pairs of beam coming from X, Y, Z direction. In terms of the dimensionality of the atom fields, it's actually now zero dimension, right? The atoms are confined in all three directions by very strong fields. Omega X, omega Y, omega Z are all going to be very strong. So it's a kind of a zero dimension, but a three-dimensional confinement optical lattice, with a very simple-minded motivation that you can actually realize this Pauli exclusion principle where only one atom, because those are fermions, can reside in one site if you make sure these atoms are in the lowest possible motional band. So therefore, these atoms will no longer come into contact with each other. They are now completely isolated. And if you put 100 rows with 100 column, 100 height put together, you can have 1 million sites. Each one has one atom. If you realize coherence time of 160 seconds, you can have a precision of 3 times 10 to the 20. So this is what I was saying yesterday. In 10 to the 21 sounded very far-fetched. But if you look at systems like this, it actually feels like, well, it's doable maybe in the next couple of decades. We will be able to get to that point where it will be 10 to the 21. We can use this to hear the gravitational waves. We can use this to explore the dark matter. We can use this to test the symmetry of the universe. This will be the most fundamental instrument mankind can make to tease out the mysteries of the space-time. Yeah?
So for these types of space-time measurements, do you only care about
Both, depending on which experiment you want to do. Okay, and I remember throughout my lecture, I told you like people who make contributions to this type of clock. We mentioned a frequency comb. We mentioned laser cooling. We mentioned single particle quantum state control. And here's another one. These three gentlemen were the first ones who created so-called quantum gas, Bose-Einstein condensate, and they won Nobel Prize. And Debbie Jing, she survived, not died away 2 years ago, she would have won Nobel Prize as well. She was the first one who created a Fermi degenerate gas. Now we are using them. So you can see the field of AMO physics have been progressed tremendously fast over the last 2 decades. Those Nobel Prizes are recognizing only a select few of some people who made tremendous contributions to the field, but it's done by a lot of people, and I think some of you included. And what's really exciting is the very best technology or science that's being developed in the laboratory is now changing the landscape how we make measurement science and measure quantum using the quantum technology. And I want to emphasize that point too. So if we had clocks like this, going back to the question the student asked, you could have actually a system like the 3D lattice clock sitting on top of the Earth surface, and we know through general relativity that space-time is distorted due to gravitational potential. So what if that you can measure the proper time at the top layer of the lattice being different from the middle layer or the bottom layer of the lattice? These atoms are spaced apart by a few tens of microns. You would never thought about the time would be different, right? When the GPS was first launched, in order to test the relativity, general relativity, people launched satellites by tens of kilometers, and they carry their clocks on an airplane to fly around the world and come back and say, oh yeah, time is different, verifying Einstein's relativity. Here, you can have a technology where just moving your clock by a couple tens of microns, the time is different. And that is actually quite interesting because you can measure the gravitational potential. Clock is sensitive to gravitational potential, but also gravity, because you can measure the gradient of the gravitational potential by layer. But what's most exciting is actually now you think about what if you're putting atoms in coherent superposition of this layer in the vertical dimension versus the layer in the horizontal dimension. You write down the quantum mechanical wave function psi xt. X and t are the two variables, parameters in your Schrödinger's equation, and usually you feel quite comfortable. X and t are independent variables, but in systems like this, t depends on x because time is different in a different x location on the vertical direction and the horizontal direction. So you could be entering a regime where quantum physics and gravitational physics have to merge. Okay, it's not quantum gravity. I'm not talking about black hole, and I'm not talking about Brian Schwingle is going to tell you about quantum information gets scrambled by gravity field and so on. Nothing about that. But a very simple-minded experimental physics where if you were the first to be able to see quantum physics is not going to be, the coherence is going to be degraded due to the gravity, surely you're going to win the Nobel Prize. So, this is the physics where people have never seen those kind of things before, right? I'm not saying that this will be done imminently. This probably will take several decades, but I do feel the technology is moving towards that direction, that you can do that. People sitting in the audience could be the ones who are going to make this happen. But anyway, this is the kind of the general vision that we have. This is the direction why making the clock so much better is not just really maintaining the time for everyone's daily use, but really it's the deep fabric of nature that we want to explore. Okay, so we mentioned of SU symmetry. Well, all these nuclear spins can play a role where they are all symmetrical and so on. And in fact, it turns out they are becoming extremely powerful when you want to use this to do evaporation. You have heard about evaporation. Fermions are not good for evaporation because they do not like to interact with each other when the temperature is too low. However, because you have 10 different nuclear spin states. They act as distinguishable particles, and they can have a very strong interactions even when the temperature is extremely low. There's nothing forbidding them from colliding with each other and thermalizing and evaporating. So we can actually indeed producing a very, very low temperature Fermi gas. So TF, the so-called Fermi temperature, and T over TF 0.05 is actually very deeply degenerate Fermi gas of those strontium atoms. In fact, 10 independent Fermi Cs, each one of them represented by one nuclear spin, all coincides in one place, and about 8 nanokelvin or so temperature. And if you load them into the optical lattice like this, you can have one particle per lattice site, and they're occupying, this is a very, very basic solid state physics picture. You probably have learned this part if you have taken any introduction to solid state physics. Is this called the Brillouin zones, plus minus h bar k, and these are the quasi-momentum space, and these are the band structure. Within the first Brillouin zone, you have the first band, second band, and depending on whether you have a tunneling or not, the band will become flat or curved depending on the tunneling coefficient, right? These are the basic physics of lattice physics. So we can put atoms all in the lowest band, as this student properly observed. We can put all the atoms right in this band, and then we can release them into space. And what you see is the atom flying apart with a plus minus h bar k worth of momentum. It looks like a square. It's really very interesting. Like if you have played with gas, right? Those are atoms coming out like a gas. And if you let them expand, they're going to fly out like this, you would imagine. Here, you let the gas go and they fly out in a cube. Isn't that funny? It's a condensed matter physics, but yet you can display this ensembles of gas atoms. It's very, very quantum mechanical, these kind of a picture. So you put all these atoms in the lattice like this, is so-called insulator, because these atoms, one each, and once there's enabling atoms there, this atom cannot tunnel because it's being blocked. So if you try to apply current, they won't conducting current here. And we can actually explore further how low the temperature is. For example, you can measure the transition frequency from the ground to the excited state, ground electronic state to the excited electronic state. And because you have all the atoms confined in the lowest possible motional states, when you drive those, you can have the motional states being the same, 0 to 0, or you can go from 0 to 1. These are those three side bands in x, y, z directions. But there is no 0 to minus 1, because 0 is a 0-point fluctuation state of harmonic oscillator. There's no state below that. So you can see the transition is very asymmetric. You have a blue sideband, there's absolutely nothing in the red sideband, indicating the atoms are actually in fact in the lowest possible band. If there are atoms in the second band, the third band, then in the transition you will have if you had a second band, then you can go from 2 to 1 or 1 to 0, and then you will have a red sideband. So when I answered the question that the student was asking, that you have different bands, and I said, yeah, they are all in the 0 band. How can I be so confident? It's because of the spectroscopy signature like this. On the other hand, you can put more atoms into, suppose this is only when you have, every atom has the same nuclear spin, but if you have a different nuclear spins goes into these optical lattice sites, then these nuclear spins can interact. The Pauli exclusion principle no longer applies because these are distinguishable particles. But nevertheless, interaction will be extremely strong, as you can tell that this is the original carrier transition with only one particle. And when you have two particles, the interaction is so strong that the frequency shifted of the clock transition is now frequency shifted to something a few kilohertz away. And this is a way to actually sort. You can use this kind of a spectroscopy to sort which cell holds how many particles. And so with only one particles, we cannot get a very long coherence time. Here we have 10 second coherence time. If I have time today, I might actually get to the bottom, to the end of my talk. I will explain to you what's limiting the 10 second and how do we get to the 160 second that I promised you from yesterday. We can also put a microscope.
What was EG minus in the plot?
Say it again.
EG minus in the
Oh, sorry. Yeah, I went ahead really fast. The EG minus and EG plus is, remember when you have a 2 degrees of freedom, when you have a nuclear spin, so now the motional degrees of freedom is all gone. Maybe it's actually worthwhile to go back to the very beginning of my talk. Remember I showed you this particular slide about 3 degrees of freedom. And this is the early time when I was telling you about in the a stack of pancakes traps. It's going to come up in a second. Yeah. Remember I told you about 3 degrees of freedom, nuclear, electronic, motional degrees of freedom. And I explained at the time, if I put an all nuclear spin into 1 degree of freedom, electronic into spin triplet, electronic degrees of freedom into spin triplet, then the only motional degrees of freedom can be anti-symmetrized. Now, in the 3-dimensional optical lattice, they are all occupying, every single atom is occupying the lowest possible state. So there can be possibility of NN minus MN. It's all single state, motional degrees of freedom. So there's nothing left. So this column goes away. You have these 2 degrees of freedom has to be made at spin, so-called anti-symmetrization for the total wave function. So what you can have is either the nuclear spins is symmetrized such that electronic degrees of freedom is anti-symmetrized, or vice versa, or the nuclear degrees of freedom is anti-symmetrized, electronic degrees of freedom is symmetrized. So therefore there's EG plus, EG minus, indicating EG plus is this, EG minus is that. And they have actually different interaction energies. And you can tease this all out. So it's no longer, all I'm trying to give you the impression is we can use mathematics to describe what we are talking about. You know, textbook, you write beautiful quantum mechanics textbook. What's really beautiful is in the lab, you do this exactly as textbook. And you discover new technologies that can do exactly textbook type of experiments. So it's no longer anti-symmetrization is just a mathematical construct. It's a real consequences. You see frequency shifts like that.
By the way, the trap wavelength doesn't depend on the nuclear degree of freedom.
That's correct. Yes. Has a little bit of dependence, but not at this level, as the so-called tensor product, but I'm not going to go into that detail. Okay, so I was about to tell you about that we can also take, put a microscope on top of this quantum gas. You can take pictures of what's going on. And so here's your 3-dimensional optical lattice clock, where you have 3 pairs of laser beam coming together and forming interference patterns. And you can put a microscope on top of it there, just like as if you're taking samples. And what's really nice about that is that you have a picture like this, or these atoms are trapped in the 3-dimensional confinement. And you can just take a picture such that you can actually see the excitation fractions of atoms inside the 3-dimensional optical lattice. And what's really nice is you are essentially visualizing, now really truly dream come true. Every atom is a little clock, and you're visualizing them, all of them simultaneously. And you can actually measure the correlation functions between different regions of the 3D lattice. If you want to measure the field gradient and so on, you can just do correlation spectroscopy to figure that out. And the measurement, for example, this is the actually powerful example. Suppose my magic trap is not magical. I think Lian was asking me yesterday, how well can you control? And I said, well, 10 minus 18. How can we be sure? Suppose these wave, the trap frequency is slightly off, such that the polarizability of ground state and excited state are slightly different. We can take an image, and you can immediately see, well, looks like a Newton ring type of thing, because of in the center the atom is exactly on resonance, going out a little bit, it's no longer on resonance, going out a little bit, you'll see another resonance. And this is telling you that these traps are not exactly matched. If it's matched, you will see no change. So that's one picture. If you want to apply a very small magnetic field gradient, such that this row of atoms to that row of atoms, that row of atoms will have a slightly different Zeeman frequency shift, And you can take a picture and you see stripes, atoms in resonance, off resonance, resonance, off resonance, and so on. So just one picture will tell you the atom light coherence is being frozen into the atom. And we can actually now measure down to 10 to the minus 19 after 3 hours in terms of the clock evolution. This is the picture I showed earlier, that you can use this technique of being able to use the frequency shift when you have multiple atoms occupying the same site. You can use that spectroscopy sequence to select a shell of atoms. Well, here's, for example, in the inner core, you have 5 different atoms occupying the same site. Outside a little bit, you have 4 atoms occupying the same site, 3 atoms occupying the same site, and so on, until to the most outer shell, you have 1 atom per site. And you can just, because the frequency is all distinguished, right? As I showed you pictures, where you have the carrier clock transition here, and if you have 2 particles, the 2 plus and 2 minus is different, as I was explaining, Eg plus, Eg minus. There's similarly, you can think of EGG plus, EGG minus. There's always a symmetrization and anti-symmetrization of electronic diffuse freedom due to the nucleus being correspondingly being anti-symmetrized or symmetrized. And by just putting the laser frequency here, you can select the 3 atoms in a symmetrized fashion, and it, boom, take a photo. And these are how the atoms are distributed in your system. So these are great ways to select atoms and study 1, 2, 3, 4, 5, how atoms are interacting with each other and how complexity arises. Finally, I think you do have maybe a couple minutes left to tell you how do we think we can go to 160-second coherence time. We are now trying to do that experiment, and that's a little bit of challenging, but let me tell you how we are going to do that. We load atoms into the lattice, and turns out the lifetime is greater than 100 seconds. So that's a necessary condition, not a sufficient condition. It's necessary. We need to put the atoms there and in the ground state. They do live there very long, so that's good. When we put them into coherent superposition between ground and excited state, what do we find? That the coherence decays away after 20 seconds. And that's a major limitation. And it turns out this major limitation comes from the fact that when we observe the atoms in the optical lattice, we can actually see the ground state atoms actually gaining population, while the excited state is losing population. So somehow excited state is decaying down to the ground state. And the first reaction you have may be, oh, that's completely natural. What do you expect? You put atoms in excited state, they're going to decay down to the ground state. Except these atoms are special atoms. Remember, the excited state atom lifetime is 160 seconds. They shouldn't be decaying this fast. And it turns out the reason is actually the magical wavelengths. We call it magical wavelengths. Magical wavelengths is not magic after all. In fact, it does a little bit of a Raman scatter, where the excited state atoms can scatter off the upper lying triplet families of states and emit a photon such that the population is now decayed back down to the ground state, while the ground state is far off removed from other resonant states that the Raman scattering probability is much, much smaller. So this Raman scattering is what's limiting the lifetime of the excited state. And so the solution to that, to solve this problem, is that we must reduce the lattice intensity, because obviously it's the intensity of the laser beam confining these atoms a little too strong that's driving them through this Raman process. But we have a problem, right? So this is the remember I was telling you about spin orbital coupling? Now that's going to play a role here. If you have one fermion, so let's simplify the problem. You have one fermion confined in 2 wells, and this fermion can jump back and forth because the lattice, as I told you, we can put up lots of intensities. The lattice is very deep. The atom won't jump, won't tunnel, and that's good, except the Raman scatter is a problem. Or you can say, well, I want to lower the lattice steps such that the Raman scattering is no longer a problem, but then the atom is going to tunnel back and forth, and that's going to cause a problem, because as the atom goes from left to the right, the wavelength of the optical laser that's probing the clock transition has a different phase shift. Remember that I told you about e to the I phi phase shift in the spin orbital coupling? So that means this atom in the left is going to pick a different phase shift than the atom in the right, and that phase shift is going to cause a mistake in your clock. This is nothing but Doppler shift. If you think about when the atom is moving through the wavefront of the laser, you'll have a Doppler shift. So this gives rise to an easy solution you can think of. That is, if you rearrange the distance between the two wells to be slightly larger, such that actually lined up with the nodes and antinodes of the clock laser wavelengths. Suppose you have a way to pull up these two traps a little bit, then as long as the phase is exactly matched, e to the IKA equals to 1. So if the wavelength of the laser that's probing the clock transition equals to the half the wavelength of the laser that you use to create those traps, this prefactor e to the IKA equals to 1, then you get into this very funny business where the atom can be jumping around back and forth, but there's no Doppler shift. It's kind of strange. When Doppler shift is usually associated with motion, but here, because the motion is quantized, you can only go to two places, and the phase shift is the same. The Doppler shift is 0. So that's easy enough to understand. Right? Everyone can capture that concept very quickly. Experimentally, how do you do that? The wavelength is fixed, 13 nanometer. Remember, that's the magic wavelength. We have to use that wavelength because that's where the polarizability of ground excited state match. In order to change the distance, then all we need is, instead of retro reflection that I was talking about, putting a mirror here, you can actually have two beams coming in with a slight angle. When the two beams come in with slight angle, the interference is given by the wavelength divided by 2 sine theta over 2. Theta is the angle intersecting the two beams coming in. So by varying the theta, you can actually get this exact condition, e to the IKA equals to 1. Now here's the difference between theorist and experimentalist. Theorist at this point, like a Graham, sorry, putting you on the spot, you will say this is good enough. Yeah, it looks like clearly this is a nice solution, and you can just control theta such that this is exactly equals to 1. Experimentalists have to worry about how well have you control the theta. And it turns out, in order to make sure this is exactly equals to 1, the theta is somebody, you, in the lab, does it, controlling that angle. And there's a certain level of precision or accuracy you can control these angles. If you tell me that I want to maintain two laser beams intersecting with each other with 1 microradian worth of precision day after day, that turns out to be actually very challenging. And if you don't do that, that means this thing, e to the IKA, can vary. Because remember, k is a 2 pi over lambda of the clock laser, but a is very much related to this angle theta. If theta fluctuates, a will fluctuate, this phase will fluctuate, your clock frequency will fluctuate. And so that's a problem. It just means that it seems like a very daunting experiment to do, to make sure the theta to be that well precisely controlled. But turns out there is another ingredient. Here's another, the theorist will come back to help us figuring this problem out, saying, well, actually, all you need to do is, instead of having just having one atom too well, you have too many degrees of freedom. Let's fill them up. Let's put out 2 fermions, 2 wells. If that's the case, even if the distance is not as good, even if the theta is fluctuating a little bit, but the fact that when the particle tunnels from left to right, the two particles are going to interact very strongly, it's going to make this probability, the perturbation probability, to be very small if the tunneling rate T is much less than the interaction energy U. This becomes a second order process. So all you need is to make theta to be reasonably good, such that the distance between them roughly matches with lambda of the clock laser, and the rest is just using this the so-called super exchange interactions to take care of the business. So the particles won't tunnel. In fact, they will stay put like this. So this is what we are working on at the moment to try to get to this longest coherence time. And finally, it turns out when you say, okay, now you have a grand scheme of things worked out. These particles are going to be individually loaded, and due to the band insulator physics, they are no longer moving around. So everything should be good, except there's one more thing. And I'm sure it's more than just one more thing. There will be multiple things. That's what the science never ends. You keep going, you keep driving, you'll discover a new layer of problems and exciting discovery opportunities. For example, when you are driving these atoms from ground to excited state, this goes back to my lecture 1. these atoms becoming radiating dipoles. They are being driven by electromagnetic field, and there's a partner sitting just one wavelength away, and there's so-called retarded potential. You have all heard of this, right? I'm sure you have all solved Green's function, being 80% of you are theorists. So this little dipole is going to have a retarded potential interacting with that dipole, and that dipole is going to interacting with that dipole. In fact, all of them are going to be interacting with each other because they're being driven by a common laser field. So this actually gives rise to very, very classical problem, actually very interesting problem called a collective dipolar coupling. And the real part of it, some people call it Lamb shift, and in our case, it would simply be clock shift. You will measure it. We'll have to figure out a way how to drive these kind of a dipolar coupling such that we can manage the clock shifts, just like we did when the atoms were interacting, when they were running into each other. The imaginary part is the so-called line broadening, or you have heard about super radiance, is exactly what Bob Dickey back in 1950s were imagining, that if hypothetically you can have an array of dipoles, hypothetically, arrange them in orderly fashion, then you can have collective radiation. It's no longer hypothetically. This is happening in the laboratory. These dipoles are there, and we do not obviously want superradiance, which used to be a very novel aspect of research for people to see. Individual dipoles coupling to the vacuum field is causing this spontaneous emission. Who would have thought? But it took Bob Dickey to first propose, these particles can actually be collective, such that the enhancement of the decay can be beyond the coupling of individual particle to the vacuum field. And here, this would be just part of the ingredients of the clock. As you concur to the next decimal point of the clock accuracy, these are just by the way problems you have to study. But turns out, these are the problems some young faculty members building their experiments just to study one of those problems. So here is where I think an excellent opportunity to think of being able to combine pushing the measurement precision forward and use that to study interesting scientific problems in many-body quantum physics. So this also is a good place to end, because these kind of a dipole-dipole connection is exactly what I want to talk about tomorrow when I tell you about ultracold molecules. And there it's all about dipole-dipole interactions and so on. So there's a connection there. And I also want to give you just a quick slide on, since I didn't acknowledge people yesterday, here's the graduate students and postdocs over the years, and our theory collaborator, Anna Maria Ray, and many past group members who have contributed to this strong team that's been running for the past 18 years or so. But it's been quite a nice drive in terms of figuring out all these maximizing quantum coherence, use that to study quantum many-body physics, connecting to quantum information science, and so on. Thanks. Other questions? I like very much this very interactive atmosphere here in this classroom. Yeah.
So when you have these spin-over interactions, and then you also discuss some of the SUN physics.
Yes.
So is there anything interesting that comes out when you consider these two together? Because they're different degrees of freedom. So in principle, you could also try to couple them.
Yeah. So we haven't really solved, for example, one of the classical problem that we would like to solve is to study is SUN condor lattice problems. We haven't done that yet. So far it's been, you can also study SUN. This large SUN just means there's a very large quantum degeneracy, and so you can use that to study how the entropy flows from different subsystems of a interacting quantum system. There's an array of things that we can study.
So for the dipole case, can you use a dynamical decoupling?
Yeah, so this is exactly what we have been talking, our common friend Misha, a lot, maybe also with you, to really figure out navigating a path where all these dipoles are interacting. There must be a way to drive them such that on one hand it can be very interesting, phase diagrams you can use, but on the other hand, a very clean path for clock. That's actually fascinating. I think it will be very, very great opportunities for studying, because the system is so clean, right? And we have lots of patience. We don't need to do Rydberg physics that everything is done in microsecond. Let's take a 10 seconds or 100 seconds to study this, but because everything else is controlled. There's no other deep single particle physics. Yeah.
I was just wondering, in the optical lattice, the 3D, like, do you have depth resolution?
Not yet. No, right now we don't. And the resolution will come from what we designed is having a magnetic field gradient such that you can apply gradient, so you can do layer by layer like a tomographic imaging. So if you imagine apply a big field gradient such that this layer of atom sits at one magnetic field, the next layer of atom sitting at a different magnetic field, and if the gradient is big enough or your spectroscopy resolution is good enough, you can actually, your laser will go in interacting with only one layer because the next layer is already magnetic field shifted away from resonance. This is actually kind of in the spirit I showed you, the fringes. When you remember I said apply a magnetic field gradient, you can see fringes one at a time. Those fringes are not single layer fringes, but if the gradient is a little deeper, then you can in principle get to the point where a single layer can be imaged one at a time, like a tomographic imaging. And that will be quite exciting. And this will be the first system where it's a three-dimensional system can be imaged. So far, all the quantum gas microscope experiments are 2D systems. Yeah.
You mentioned several times this 160 seconds about this coherent time. Why this 160 seconds is so special?
And nothing special. It just turns out to be the atomic property of strontium. It was given by the universe, depending on how you think about it. It's just the way that nature configured it. There are atoms which can have longer coherence time, and it will be interesting to explore. In fact, 160 seconds is kind of a funny thing. When we started 18 years ago, at that time, the best laser you can have is 10 hertz or so wide line width, or the coherence time is not tens of a millisecond. So 160 seconds sounds fantasy. This is way too long, and it's like similarly like I laugh about some experiments going on in Germany. People actually use single trapped ion, and their lifetime is a year. So you obviously you'll never be able to have a quantum coherence for a year, at least for the foreseeable future. But nevertheless, they actually do very, very nice research with ytterbium octopole transitions in the single trapped ion. So back in 2000, indeed, we were thinking of 160 seconds. That's going to take a long, long time to get there. And especially even laser, and as well as on the atom side, how do you maintain that quantum coherence? But as you hear, right, even today, we are getting close. We are actually not only a factor of 10 away, essentially, from where we want to go. Yeah?
So if maybe related to that, what are the experimental cycle times? And if you have a very long probing time, does that mean that
Yeah.
the graduate students need to stay in that for a very long time?
Well, the graduate students are cheap labor. They should stay as long as they can. Yes. What's the rush? No, that's an excellent question. In fact, the duty cycle is a tremendously motivating factor for new technology we are developing in the lab. For example, we are now doing optical evaporation of fermions that used to take 15 seconds to evaporate. Now it only takes 2 seconds in evaporating all the way to the degeneracy. So that's great. If you only need to wait 2 seconds, if you could get into the regime where 160 seconds is your useful time for doing experiment, and then you have to spend 2 seconds to re-prepare quantum state, and you get to spend another 160 seconds to do experiment, that's pretty decent duty cycle right there. So you're spending 1% of time to do something kind of a bookkeeping. The rest of the time you're actually gaining something. The current duty cycle is not that favorable. I think it's a 50-50. We spend 50% of the time preparing quantum state, 50% time doing actual useful experiments. Yeah.
So is the goal to prepare entangled many-body state using the second order doubling and dipole coupling?
We would love to. In fact, there are a very strong discussion with Anna Maria Rey's group right now that we think we can prepare cluster entangled states in the 3D optical lattice. Yeah. Maybe in the next summer school we can discuss that. Okay. Yes.
Can you comment like about temperature of these?
What temperature?
Of the firmament.
Atoms? Yeah, the temperature ranges from a few nanokelvin, 5 nanokelvin, to a few hundred nanokelvin.
But you're not looking to make it even lower. That's not.
Yes, lower only in the sense of yes. So when I showed you the picture, when every looks very, very idealistic. Every lattice site is occupied with one atom, with no hole. That's obviously not something we can achieve today. That means there's no entropy, right? Entropy is equals to 0. Right now, entropy is per particle is still finite, 0.2 kb on that level, and so we are obviously very interested in getting lower and lower in temperature, and there are ideas out there. People use dimple traps in the middle, and they use evaporation of the very shallow traps outside. You can continue to lower the entropy and so on. But we'll be very interested in studying, say you have a 10% hole in your system. You have an optical lattice, 90% of the cells are occupied by a single particle. There's 10% hole. So this would be, in some sense, in quantum information, we talk about error correction. Here is something which there would be a problem, but is that a possible? Again, you think about ways to make the system more robust. So even in the presence of the hole, we can preserve this kind of no tunneling regime. And these are the studies we are undergoing right now in collaboration with the theory. Because there will always be some entropy left, and how do you do your measurements in the presence of that finite entropy is a key question. Yeah.
So in most of these experiments, you're using fermionic isotopes of strontium. But some of these, for example, getting a Mott insulator and those types of things.
You can use
also
boson.
work with bosons.
Yes.
So I guess in principle, for that, like you could still do a clock with bosons. It's just that fermions work as well.
With bosons, for strontium, for example, remember the boson, actually, that transition is forbidden as 2,000 years. And you would need to use magnetic field to mix the states. And the magnetic field could introduce noise. So yes, I think in principle, when we were first designing the experiment, when things can collide with each other, the bosons and fermions makes big difference. But now, as you correctly pointed out, by the time now we are talking about insulators, then indeed the bosons could also work, except the band insulator, however, still requires this to be fermion. But you could imagine you can just use J square over U term to make yourself to be in the Mott insulator regime. But what's really kind of interesting now is we are using this funny condensed matter language, insulators, Mott insulator, to describe atomic physics, atomic clock, which is traditionally very atomic physics, right? Precision measurement. And that's the exciting aspect of the field. There's this combination of different intellectual fronts into one single quantum system. Okay, so I think I'm way past the time that it's great to have those discussions, but we can see you again tomorrow.